what we want to do next is we're going to talk about continuity. So we're going to say that let's let f be a function from g to c. Then f is continuous at a point z naught in g if the following. I'm going to go slightly backwards from the book, but I'll explain. So f is continuous at z naught if it satisfies the condition according to epsilons and deltas as follows. So if for all epsilon, there exists a delta so that for all values z and g with 0 less than z minus z naught is less than delta. Oops, and I don't want the 0 here. So just z minus z naught less than delta, then f of z minus f of z naught is less than epsilon. Okay, and so this is very similar to the limit definition, except that our limit is f of z naught. So the first thing that I want you to notice, and this is a definition of what it means to be continuous, but f is continuous at z naught in the domain of f if the limit z approaches z naught of f of z equals f of z naught. Right? That's essentially what that says. Or if z naught is an isolated point. Okay, isolated points are, in a certain sense, the opposite of accumulation points. Accumulation points are points such that no matter what open disk you have centered at that point, there's some points in G that are inside that disk. Isolated points are points such that there exists an open disk centered at the point where there's no points in G in it. Okay, so that's an isolated point. But notice that if z naught is an isolated point, then this condition is true because we say for all points in z with this condition. Well, if the only point where this happens is z naught itself, then everything is fine because z minus z naught will be 0. F of z minus f of z naught will be 0. So this is all true. So we get to include isolated points for free based on this definition. Okay, so the way that the book says it is that a function's continuous if z naught is an isolated point, or if this happens, okay, or if the limit of f as z approaches z naught is equal to f of z naught. Okay, so that's continuity at a point. We say that a function f, so let me be a little bit more precise here. Let's let f be a function from g to c. So let f be a function from g to c. Let E be some subset of G. Okay, so let E be a subset of G. Then F is continuous on E if F is continuous at every point in E. So if F is continuous at every point in E. So we've only really defined continuity at a point, but if you want to talk about continuity on a set, that means that it's continuous at all points in that set. So just as a few examples, I'd encourage you to go through and let's look at 1 over z as z approaches z naught. And it turns out that that's going to be 1 over z naught. Okay, and so I'm not going to walk through the argument. I've basically already done the argument when z naught is I, but the general case follows exactly like that. So this tells you that f being 1 over z is continuous on its domain. So it's continuous on c minus 0. Okay, and most of the usual functions that we'll work with, like 1 over z, z squared, squared z we have to be a little bit careful of. e to the z and log z, we have the branch cut issues to deal with, but all functions are going to be continuous on their domain, with the exception of some branch cut issues. So we'll get into some of that when we talk a little bit more systematically about these functions. But that's what it means to be continuous. So continuous means that, again, the limit of f is z approaches z naught is f of z naught, or z naught is a isolated point. Okay, so that's what it means to be continuous at a point, and then continuous on a set means that it's continuous at every point in that set.